My name is Taylor Cease, Research Associate at South Dakota State University, and thank you for tuning into this webinar, providing an overview of some of the capabilities of CFD and potential use in product realization and research and development activities. Other collaborators on this webinar include Dr. Stephen Jett and Scott Dupre. Computational fluid dynamics, or CFD, has seen increasing popularity in recent years as a cost-effective and time-efficient method of evaluating prototypes, analyzing product design, and testing system parameters in a non-destructive manner. CFD uses numerical methods and algorithms to solve and analyze problems involving fluid flows. The software does so by taking the 3D geometry and dividing it up into thousands or millions of cells, called a mesh. Then, taking user inputs like inlet flow rates, material properties, and boundary conditions, the software calculates the bulk flow characteristics by calculating the flow at each individual cell and how that output affects other cells around it. This can be done for both internal flows, like pipes and ducts, or external flows, like flow over a boundary or surface, for both liquids and gases. In using computational fluid methods to solve problems like these, there are several advantages that are gained over experimental testing. First of all, series of numerous simulations can be run quickly and cheaply, reducing the material resources required for multiple experimental testing apparatuses, or eliminating the human element required for a clinical trial. Additionally, computational results can provide an easily digestible output for analysis of some parameters that are difficult to visualize and measure in an experimental setting. For example, turbulence is difficult to visualize, particularly for gaseous flows. Also, near-wall parameters like shear stress are difficult to measure properly in an experimental testing. CFD can provide color-coded images to more easily grasp the advantages that one product design may have over another. Additionally, CFD has an extensive list of other parameters that can be tested for and monitored during simulations, such as heat and mass transfer, chemical reactions, or multi-phase interactions, among many others. Many high-profile organizations have begun to view CFD as an integral part of the product realization process. For example, the Food and Drug Administration, or FDA, has long used a flow chart for how a product goes from ideation to a commercially available, approved product. Within the steps of this product realization cycle, the use of CFD has been included as valuable supporting evidence throughout numerous stages. For example, while CFD can be used during the prototyping phase to improve product design, it can also be used extending into clinical trials and regulatory decision as a means of verification and validation of the results obtained there. This helps reduce the dependency of product design on extensive human testing, as CFD provides a scientific basis of product intent, functionality, and expected performance. Additionally, CFD has important uses beyond the product realization cycle into the post-market stage as a decision support tool for real-world cases. CFD can be used to provide the scientific evidence behind product design and selection in potential insurance claims, litigation, etc., stemming from product issues observed or experienced by customers. It can also be a valuable tool for commercialization and marketing of these new products as they go to market. One of the overarching goals of this webinar is to introduce you to some of the capabilities that CFD has to offer in testing of products and systems, particularly stemming from examples of CFD projects that SDSU has conducted over the past decade. In doing so, we hope that some of the outputs and results that are presented may be relevant in one way or another to your current research, development, and marketing of products, systems, and processes. In doing so, SDSU would be more than happy to discuss any interest in any of these functionalities displayed here and potential collaboration on projects in a partnership between industry and academia. Contact information for the SDSU representatives to discuss these options can be found at the end of the webinar. One of the most basic, yet often most valuable, outputs from CFD simulations is demonstrating the velocity profiles of the fluid through the system. In an experimental setting, velocity measurements are limited to singular points based on where the probe is located, and overall fluid flow profiles are often difficult to visualize especially for invisible gases. CFD allows you to visualize the bulk fluid flow and easily take measurements at multiple points within the system without the need for multiple pieces of hardware. These images can provide a quantitative analysis of each system, allowing the user to make general overall observations of the fluid flow patterns and begin investigating design changes that could optimize these flow trends. In the examples provided here, the left images show a biomedical comparison that was made between 4 different thoracoabdominal aneurysm repair devices. These qualitative results were able to show where stagnation, flow separation, and recirculation of blood flow may be located due to implementation of each of these devices, which can lead to issues with clot formation and delayed nutrient supply to arteries, among other things. On the right, velocity streamlines were tracked throughout the entire aortic arch and descending aorta from a CT scan that was received from a biomedical device company. This image was used to initially diagnose how an aneurysm on the aortic arch was causing excessive mixing and inefficient blood supply to the descending aorta, which would typically result in requiring the arch to undergo a stent installation as a repair procedure. However, while the fluid flows through the system, we are often not only concerned with the overall fluid flow patterns and velocities, but we are also interested in how the fluid interacts with nearby boundaries. While bulk flow profiles can at least be attempted to be visualized in an experimental setting via high-speed videography, dye tracing, smoke tests, or other methods, many of these fluid-to-boundary interactions are very difficult, if not impossible, to measure accurately during tabletop prototyping. CFD provides a method to calculate these parameters based on the flow profile induced through the system, which allows the user to visualize and quantify things like wall shear stress and near wall residence time, which they might not have been able to properly analyze before. In the examples provided here, the left images show the same biomedical devices for thoracoabdominal aneurysm repair as shown previously, but now analyzing the blood flow close to the device boundary and how it might affect the nearby arterial wall that it communicates with. Time average wall shear stress is essentially a representation of the degree of flow near the wall over a typical cardiac cycle, where high shear stress can cause premature device failure and fatigue, but low shear stress can cause platelet accumulation and clot formation. Oscillating shear index is a measure of the degree of stagnation and recirculation near the wall boundary. High oscillating shear index shows locations that are especially in danger of atherosclerotic formations occurring, reducing the vessel diameter and increasing the potential for blockages. This research found that long, gradual sweeps of the arterial branches helped keep wall shear stresses at a healthy, moderate range, while also reducing areas of slow oscillating flow to reduce the potential for artery blockage or occlusion. On the right, similar parameters were used on the aortic arch aneurysm, as shown previously, to try to predict where thrombus might be expected along the aorta. Comparing these predictions to a CT scan of the thrombus that was received from the biomedical device company, low wall shear stress and high oscillating shear index did indeed appear to predict several locations of significant thrombus accumulation near the aortic arch. Additionally, another parameter of relative residence time, which is essentially a measure of the combination of low wall shear stress and high oscillating shear index, also predicted another pocket of thrombus accumulation that was shown in the patient scans. This provided some verification and validation of these parameters as useful computational predictors of real-world clinical outcomes. While most of the analysis demonstrated thus far has been focused on outputs at a specific point in time, or parameters averaged over a specific length of time, CFD also provides the ability to track how parameters vary over a period of time to create trends in non-steady state situations. For example, the images provided here show 2 cases of an intrasaccular aneurysm repair device being installed in various aneurysm sizes and shapes. Using a point monitor, trend lines were created to analyze the pressure difference created across the device neck by a pulse of blood flow to evaluate the fluid forces placed on the device. This output allowed the research team to verify and validate their numerical calculations and estimations in a non-trivial bifurcation flow system, where significant energy is lost at the bifurcation compared to a typical straight line flow jet calculation. This analysis also demonstrated how the parent vessel geometry feeding the blood flow toward the aneurysm likely plays a significant role in the amount of force applied to the device, as a smaller vessel would tend to generate higher velocities focused at a smaller cross-sectional area, leading to increased stress placed on the device. CFD provides a method of being able to simulate fluid flows through very large structures and conduits, all the way down to the tiniest crevices and openings. This can be especially advantageous over experimental procedures, where these extremely tight tolerances can be difficult to manufacture and achieve during prototyping or testing. Using localized mesh refinement through the CFD software, as well as the significant computing power available through SDSU's computing cluster, simulations that might take months to run through another source can be completed and analyzed within days, sometimes even hours. Additionally, surface characteristics of a product, even down to the micro and nanometer level, can be analyzed accurately and modified relatively easily to perform a parametric study of further design changes. The example shown here was part of a study looking at drug-coated balloon angioplasty deployments in the human leg and evaluating the effect of the size of balloon inflation on the distribution of the drug as it washed off the balloon and flowed downstream. The typical procedure for this particular balloon angioplasty called for the balloon to be overinflated to open the vessel and then deflate the balloon slightly to allow the blood flow to begin to wash over the balloon. The balloon to vessel distances on these simulations range from 0.3 of a millimeter all the way down to under 1/10 of a millimeter. CFD not only allows for a single fluid material to flow through a system, but it also allows for multi-phase flows and tracking of particles within the bulk flow of the system. This allows for solid fluid and gas fluid mixtures that are common in industry to be evaluated properly, taking into account the material properties of each individual substance and how they might interact with each other. These particles can have a variety of reactions at the walls and outlets of the simulation, such as sticking to a wall or bouncing off of it upon contact. Additionally, particles can be tracked throughout their residence time in order to analyze the path in which it travels, and they can also generate their own individual parameters separate from the bulk flow, such as velocity, shear stress, etc. In the examples provided here, the simulations at the left are two examples of the balloon angioplasty study mentioned previously, where the drug wash-off from the balloons was simulated as individual particles. These particles were coded to stick to the wall upon contact, simulating absorption of the drug into the arterial wall. This was able to show how various sizes of balloon expansion affect the final location of drug accumulation and wash-off toward the outlet arteries. It was noted that, as expected, larger balloon inflations, creating smaller gaps between the balloon and the arterial wall, keep more of the drug near the balloon deployment location. On the right, carbon dioxide bubbles were injected into a column of water to simulate a photobioreactor for creating an environment to accelerate the growth and potential biofuel generation from algae. On top, the pattern of the bubbles was simulated, and the bottom images show the experimental results from video imaging in order to compare between the two. The particles were set to escape the simulation if they contacted the top boundary, similar to the bubbles dissipating when they reached the top of the open water column. It was interesting to note how the simulation showed a vast majority of the particles simply continue upward toward the open end of the water column, but a few bubbles tend to recirculate back down into the water column and travel back toward the bubble stream, which is also noted in the tabletop experimental testing. Additionally, CFD has the capability to monitor the concentration of one liquid or gas in another liquid or gas as it is injected. This is done using passive scalars, which are essentially massless, dimensionless particles that are injected in one fluid stream and tracked along with that fluid stream as it mixes with another. The passive scalars are massless and dimensionless so that they do not have any effect on the fluid motion itself, but instead are simply a monitor of the concentration of one fluid in the presence of another. In the examples provided, chlorine and ammonia were simulated to be injected at various locations in the clear well of a water treatment plant. These simulations showed that, based on the turbulence induced by both the sudden expansion and momentum change of the fluid in the inlet pipe as it reaches the clear well, the chlorine supply reached close to its final outlet concentration even before it made its first turn in the clear well path. Additionally, the turbulence induced by the fluid going over the weir boundary near the ammonia injection location caused the ammonia concentration to balance out to a steady state concentration within a couple passes of the clear well path as well. CFD can also model temperature distributions due to heat loads or heat losses applied to a space or system. Phenomena captured by the CFD software can include all three types of heat transfer: conduction, convection, and radiation, depending on the parameters of the system. Additionally, temperature gain and loss within the system can be provided by either temperature difference of a fluid temperature coming into the system compared to the initial conditions, or by surfaces that might be providing a heat flux or temperature difference to the nearby fluid motion. In the examples shown here, column photobioreactors with relatively cool carbon dioxide bubbles injected at the bottom of the column were studied with various configurations of light guides protruding through the column, which provide light and heat to further promote photosynthesis of the nearby algae. This study determined that square configurations of these light guides promoted the most consistent temperature throughout the photobioreactor. The staggered array of light guides caused elevated temperatures towards the top of the photobioreactor, potentially inhibiting the growth of algae and drying it out. Lastly, as mentioned previously, CFD can work as an excellent tool to supplement experimental studies and provide verification and validation of the results obtained. For example, the overall bulk fluid velocity in a column photobioreactor was simulated in CFD and compared to tabletop experiments that were being run in a lab at SDSU. With no light guides present through the photobioreactor, note how similar the fluid flow patterns are between the CFD output and the bubble flow patterns photographed in tabletop tests. Both flows tend to attach to the left wall before expanding out throughout the entire column, with some recirculating through the column before releasing toward the open top of the photobioreactor. This is likely caused by the forces of the bubble drag as they flow through the fluid and interact with each other, particularly as the bubbles begin to recirculate and get caught back up in the bubble jet stream for an extra pass. While most of the examples shown so far are primarily biomedically and biologically related, some of you may still be asking how CFD might apply to your facility or business, particularly if you aren't in either of those fields. Thus, we wanted to present a more in-depth case study of something that is relevant for any business, no matter what industry: heating and air conditioning. This project is a good example of many different facets of CFD already presented here and how they can be used in combination within the same overall study. The primary focus of this study was to investigate how the HVAC system can affect the spread of aerosols breathed and emitted by the individuals in the room, potentially increasing or decreasing the risk of viral transmission from one infected individual to the rest of the occupants. In this study, heating and cooling airflows were modeled in a classroom on the SDSU campus. Not only were the thermal effects accounted for, but also the barriers located in the room in the form of students, teachers, and plexiglass dividers were implemented. Typical breathing patterns from the individuals in the room were also accounted for. In the first simulation, shown here at the left, the concentration of aerosols breathed by the instructor while speaking was analyzed to determine how effective the use of plexiglass barriers installed throughout the campus really were. These passive scalar streamlines show how the barrier tends to reduce the magnitude of aerosols spreading horizontally throughout the classroom. The aerosols tend to be slowed by the barrier and rise up due to the heat being emitted by the instructor, continuing to recirculate and remain centralized near the source until eventually escaping into the cool supply airstream and mixing throughout the room. Additionally, the research team investigated how the layout and workflow of the room might affect this aerosol distribution. Once again, passive scalar plots were used to analyze the concentration of the breathed aerosols by the teacher as they continued speaking throughout a lecture. It was discovered that by simply rotating the teacher 90 degrees to have them speak toward the return air grill in the room, and thus rotating the students 90 degrees to still face the teacher but be more offset from the teacher, the aerosols were more concentrated near the instructor rather than spreading in multiple directions throughout the room. It appears that this allows the aerosols to be more efficiently removed from the space by having a more direct path toward the return air duct back to the main HVAC equipment. Next, a set of simulations were run to conduct a parametric study looking into how the amount of supply air into the space affects the aerosol distribution from the teacher. Going back to the original classroom setup, with the teacher speaking to the south and the students facing north, it was noted that by increasing the airflow rate to the room, more airflow mixing occurred, which caused the spread of aerosols in a larger radius around the teacher. This would seem to indicate that lower airflows and inducing less turbulent mixing of the air within the space would also help to provide more efficient evacuation of breathed aerosols in the space toward the return grill, rather than recirculating them throughout the room. However, the last portion of this study required further investigation of this suggestion to determine if reducing the flow rate in the room might result in significant thermal discomfort issues. Thus, temperature profiles were generated at 3 vertical planes in the room to analyze the effectiveness of the HVAC system at a reduced airflow of 1100 CFM at various locations throughout the room. When in heating mode on a cold winter day, a few interesting phenomena were noted. First, the warm air of the space was not provided with enough CFM to reduce thermal stratification and push the warm air closer to the students. Thus, you would likely still have very cold zones near the students' legs and feet. However, interestingly, the thermal stratification appears to be reduced as you get closer to the exterior wall and windows in the back of the classroom, showing how the warm air tends to flow toward the locations of heat loss. Additionally, from the point of view of viral spread, there is a danger of lockup effect in this reduced airflow situation, as the warm air toward the top of the room may create a barrier, slowing the evacuation of the lower airflow from the space. This would tend to keep any aerosols emitted from the occupants in the room entrained for a longer period of time in the student's breathing zone, increasing the potential for viral spread from one individual to another. In cooling mode on a hot summer day, it was noted that the cold supply air drops much more quickly into the space and mixes with the rest of the room air. This significant mixing would tend to promote a more even distribution of aerosols in the space, which would likely also be exacerbated at higher airflows. Additionally, moving further away from the heating loads of the exterior windows and wall in the back of the classroom, there appears to be potential for draftiness toward the front of the classroom, even at this lower flow rate. Thus, it was determined that the recommendation for modifying the airflow provided to the space may be seasonal in nature. Instead, it might be advantageous to use other methods of viral spread prevention to limit deviation of the HVAC system from its original design intent. However, these recommendations are not all-encompassing for all facilities, as each space in a building will promote different airflow patterns based on the layout of the rooms and locations of supply diffusers and return grills. Thus, we would be more than happy to work with any business owner who is interested in undergoing a study for how they might revise their workflow patterns, modify their air distribution system, or update their HVAC equipment to try to combat the next potential viral event, or even reduce the number of sick days and productivity lost during upcoming flu seasons. Thus, take a moment to consider how CFD could potentially be applicable to any design, testing, or commercialization that is currently ongoing at your company. SDSU would gladly be a resource for discussing potential collaboration, not only using the software functionalities displayed here, but also investigating other modeling methods and outputs that could be beneficial to your specific projects. Please feel free to contact Stephen Gent or Taylor Cease with further questions, comments, discussions, or requests for consultations.